There are some additional kind of safety considerations, some which kind of need a little bit of updating to National Electric Code because, right now with code, everyone's worried about rapid shutdown and how to de-energize the conductors between the array and the inverter. Well, now we have to consider, does rapid shutdown apply to the conductors between the battery inverter and the battery? Because those would be live conductors running through the building as well. And right now, there's pretty good disconnect requirements for batteries. If the batteries are more than 5 feet away from the battery inverter, you have to have disconnects on both ends. If it goes through a wall and the batteries are on one side and the inverter's on the other, you have to have disconnects at both ends. But there's not that automatic disconnect shutdown process. Now, it can be. Your battery inverter companies sell motorized breakers. They cost about $100 each, but you can put it on a motorized breaker and automate kind of a rapid shutdown disconnect process. They have to some extent to have all of this stuff hooked in together. But now we get to this point where, well, what is the fire department to think when they show up and there's a solar array on the roof and they read the placard and they say that it's rapid shutdown compliant, but there's a battery bank there? How do they know that by disconnecting the array from the system that the energy or emergency backup system hasn't energized? Well, and the problem is for emergency backup systems, you can have a disconnect switch. But when you get into National Electric Code, there's a technical difference between an emergency system and a standby system. And the logical thing is to put this total system shutdown switch right next to your other disconnects and have it be very obvious that, this is the switch that turns off all on-site power systems. But if it's an emergency system, rather than a standby system. So if it's like for a hospital generator to provide backup respirator support, that switch has to be located in a different section than all of your mains because they don't want the fire department accidentally shutting down, everyone's respirators when they're trying to diagnose why they've been called out to site. And so there's a little bit more nuance. And then another concern about having one switch that turns down the whole system. And this one switch for the whole system, that's not part of National Electric Code, although you could see it coming with your solar array on your roof and your batteries in the control room and your service panel in the house. We need something to kind of bring it all in together. But then you get into, well, what about if there's pranksters? What if someone, sees this shutdown switch on the side of a house, runs up and pulls it just to make your day horrible? That alone could get a homeowner to say, well, I don't really want one of those. So this is, there are components now where you can have like a rapid shutdown button that not only disconnects the arrays, but also disconnects the batteries and all that. There's products out there for that, but they're not really part of code yet. And for that matter, they're new products, so they're pretty expensive. Let's see, other things. You're not allowed to, batteries are a corrosive environment, so you're not allowed to have metal flex conduit. You need to have like a plastic jacket around your metal flex. DC needs to be in metal. So you do get a lot of metal flex conduit in a battery room. Let's see. You can go to the manufacturer website and piece together all the parts, but you don't get as user-friendly assemblies like you do with solar design software. All the solar design software is written for the batteryless markets. And so, again, this is where the design expertise comes back into the solar design is, being able to read spec sheets and pick out a material list from a very kind of obtuse website. You don't get that one-stop shop where you put in your array size and it tells you which inverter you need. You got to piece it all together right now. We see different sizes for the charge controllers. So, I guess this charge controller can fit up to a number 6, but our MC4 connectors can only go up to number 10. So for our array, we went with number 10. We see the array go up to a nominal 48 volts. But then again, the short circuit current, we see it at 28 amps at standard test condition. We see a maximum charge current of 80 amps going into the battery bank. And then coming out of the battery bank, it might be normally 20 amps, but it might be able to surge up to 35. Let's see. So battery inverter warranties are not the 10-year warranties of the rest of the industry. You can get monitoring systems that network everything together, which I would strongly recommend. Like one thing that kind of surprised me is with the battery inverters, they're so not consumer oriented that you actually have to buy external displays for them to make them more useful. So they're you're more likely just to get an inverter with a couple of lights on it rather than something that really tells you what's going on inside of it. Sometimes you need to spec out a transformer because the inverter systems are only 120 volts. So let's see. The Tesla Powerwall, 3.3 kilowatts of power, 6.4 kilowatt hours of output. And this is what's surprising about the Tesla Powerwall. 6.4 kilowatt hours isn't very big. And then on top of that, it can only output half of that, which means it could run at 3.3 kilowatts for 2 hours. It can't run at 6 kilowatts for 1 hour. It doesn't have that output capacity. And so, what that means is that you're only going to be running at about 10 amps out of your Powerwall. Like 10 amps? Aren't the breakers on my service panel 20 amps? So are you telling me that it's Tesla Powerwall can only power one breaker on my service panel? Well, yes and no. It depends on what you're pulling. Often you're not, your circuits are never running at 20 amps because otherwise they'd be flipping their breakers. But what it does mean is that, the Tesla Powerwall, you get one of them and you only get 9 amps out of it. What that means is during the day, you get the amperage from your Powerwall and the amperage from your array, but at night, you really only have enough power to run your refrigerator, and that's about it. So it's still not a great backup solution. It's just a feasible backup solution. So here you get into reading inverter specs and you have a continuous output of 6.8 watts, whereas you have a 30-minute burst mode of 8.5 watts, and then even a 60-second burst mode that's almost twice the power of the continuous output rating. And so what that might mean is that the inverter is only putting out 20 amps of power normally, but it could surge up to 52 amps. And so you need to check that because you need your breaker size to be larger than its surge rating, because then otherwise you'll flip your breaker when it goes into that surge mode. Let's see. And of course, there's a DC side too. Most of your battery inverters, you're going to be putting a battery temperature sensor on it. If you're tracking the energy in, the energy out, and the temperature of the battery, that's how you really get into knowing how many cycles your battery has on it and therefore what kind of life can you expect. Otherwise, if you don't know that kind of data, it's really anybody's guess, since your battery can be operating within that voltage range. You have to get down into like the microscopic level of examining halfway through its usable life battery to get a precise estimate on how much longer it will last. So it's important to track all the statistical data about the battery operation. Let's see. These are just some battery spec sheet items. We really don't have time to go into all of it, except to say that the battery inverters have multiple modes of operation, and so you can tell it, when to dump power from the battery bank based on time of day. You can tell it to dump battery based on the current range. So if you have your facility on a building energy monitor, maybe you program the building to communicate with your smart meter, so that if your building is drawing, no more than 200 amps of power, and if it draws more than that, the battery bank turns on. So it measures the current for load leveling. It also will monitor the battery voltage, and when that battery voltage begins to rise above its nominal 48 volts, it'll start draining the battery proportionately, so that you're selling the surplus energy. And it'll also even adjust in the selling mode, so that if it starts selling too much energy, it can dial back the frequency and dial back how much it's selling. So there's some utility features in there, some commercial features in there. There's a quiet mode where you can press a button and the maintenance features won't turn on if you don't want to listen to it. And these are all pretty typical amongst all the major battery inverter manufacturers. Mainly the only differences that I saw were the 600 volt charge controllers, and then how many grid inputs can you have? Can you have an input for both a generator and the electric grid, or is there just one input? And your battery inverters are kind of custom built together, whether or not you want one or two. They're kind of intended to stack with each other in kind of straightforward, logical ways. You can find vendors pre-wiring them. They're meant, you go into the project documentation and you get things like what all the features are, the conduit knockouts, the wiring diagrams for how to parallel wire them together. So yeah, it's technically, they're more ambitious than a solar project by themselves, but your manufacturer is there to support you on how to wire the very complicated wiring systems up. Even when you get into larger arrays and microgrids. So anyway, we are fast approaching the end of the program here. It's 2:15. Let me see if there's any kind of important slides here. One thing to remember is, if you're doing a solar array now, so here's a residential solar array we built for Half Moon. The plan is later on to swap out this junction box with a transfer switch, and then to put a battery inverter right next to it, and then on this side is the garage. So we'll put the batteries in the garage, the battery inverter on the wall right next to the solar inverter, maybe expand the solar inverter as well, and put a transfer switch here down the road. So in terms of making the projects kind of solar ready, it's more just making sure you have the space for the battery inverter and solar inverter. Anything else? You have the core slides. Energy Toolbase is the software for commercial battery bank management for load leveling, and they do economic modeling as well. And they have your utility rate structures programmed in. So they can take your demand structure, your building energy use, the solar array itself, and then come up with an optimal system size to where you go larger in this example, you go larger than this, and you start getting into diminishing returns. So anyway, for as far as battery incentives go, the only markets that I know that have battery incentives are California, New York, and I think Maryland has a very limited corporate tax incentive as well. But New York and California both have battery incentives. That's where the battery market is today. But I can tell you, as far as battery pricing goes, Tesla has stated that they're already at about $190 a kilowatt hour in hard costs. So that puts them, in 2017, well at the bottom of where they're supposed to be in terms of price. In fact, Tesla, the battery company, made a profit the quarter before they bought Solar City, which had a lot of debt. So they were kind of heading towards profitability before that point. And this is typical of what we saw in the solar industry too. When manufacturing is growing exponentially, you get these hiccups where the demand might not be quite as ahead as all the new volume that's coming to market. And the manufacturing costs were well below what the industry projections were, because it's very difficult to project where a market's going to end up in an exponentially growing market. And so we're getting to the point where by a decade from now, they think that lithium-ion batteries will be ready for mass adoption. And right now, it's just identifying those markets where you have a high demand rate, or your utility grid build out fees are expensive, to say, well, that's where we can start doing batteries now, or selling it to a luxury kind of oriented system owner. So that's the end of the program. I don't think there's anything in what we just went through that's not in this course. It's just a little bit more up to date with budgetary information. The one thing in the handout, the battery management system handout in the course handouts page, one thing that it does reference, it's kind of slowly downloading, but the only thing that we didn't reference that's in the handout, let me just Google for it and I'll post it to the chat box. Yeah, so there's this battery professor, Jeff Don, who, what I said about how you can't really determine how much life is left on a battery bank. He says that this is a problem with testing, because when they're testing a battery, they're charging and discharging it much more quickly than what the battery will experience in the field. And so he developed high resolution testing machines where they could actually determine the actual degradation of the battery at a microscopic level. And shortly after lecturing on this concept, he got a job offer at Tesla, heading up their battery research. And so anyway, he's very bullish on the ability for research and development to further improve the life of lithium ion. In the research and development end, they've tested anodes that can be cycled 100,000 times without degrading. And so there's, it's all about having the right chemistry so that the battery anodes don't get covered up with plaque, which inhibits ion and electron flow through the battery. So anyway, if you're more interested in that, research Jeff Don. His lectures on YouTube. It's great. Otherwise, we're at the end of our program. So unless I see any questions, if you have any questions, ask them now. Otherwise, I'm going to pass it back off to Half Moon.
Great, thanks, JR. Thanks everybody in attendance. This concludes our webinar for today. JR is back with us every Wednesday and some other days too with solar material. Check out our website for more information if you want to register for those courses. When I close things down, you'll be kicked over to that brief quiz I mentioned earlier. If you don't want to take it right now, you don't have to. It'll be sent via email to everyone in about 1 hour. After we get the quiz back from you, we'll complete your certificates. You should have them no later than 5 business days from today. If you need them any sooner for licensing purposes, certainly call into our office, or you can respond to any of the emails we sent regarding today's webinar. We can help you out there as well. Okay, that's all I have. Thanks again, JR. Thanks to everybody in attendance. Here's your quiz.